Welcome to this week's seminar to all the viewers on YouTube as well. This week, I'm excited to introduce Daria Holdenried-Chernoff from UC Berkeley, and she's about to give a presentation that is titled Variability in Turbulent Flows and the Earth's Dynamo.
Okay, great. Well, thank you very much for inviting me to give this talk. Today, I'd like to share with you some of the work that I've been doing with Bruce Buffett and also with David King here at UC Berkeley. And the idea behind this project is essentially to try to find ways in which we can use insights from core dynamics to understand geomagnetic reversals. So as we all know, when we're talking about the Earth's magnetic field, we're thinking about the outer core and the conductive fluid in the outer core, which is interacting with the magnetic field and sustaining it against decay. And the main ways in which we observe the geomagnetic field these days is through satellite observations and ground-based observations. And supplementing these with nautical observations, we can extend our knowledge of the changes in the geomagnetic field to about 400 years. So these sources give us information about decades to centuries of changes in the geomagnetic field. However, if we want to learn about reversals, we obviously need to consider paleomagnetic observations, which give us information about timescales of tens of thousands of years or more. But generally, when we are thinking of models of core dynamics and dynamo generation, it is the short timescale information that has been used in conjunction with these. So if we look at the paleomagnetic observations, we see that we get about 4 reversals per million years. But it is difficult to use this information with the dynamo models, partially because it's difficult to run the dynamo models for long enough for it to be relevant to reversals, but also because the paleomagnetic observations are quite coarse-grained compared to what you need in a dynamo model. However, we think it's really important to try to find ways of incorporating these paleomagnetic observations into the core dynamics theory, because if we restrict ourselves to only the short timescale information, we can make an analogy with climate science and say that the timescales involved are almost like trying to create a climate model that spans hundreds of years with information about one day of weather. So clearly this is not a great idea, and we should really be trying to incorporate more paleomagnetic observations in what we're doing. To make matters even more difficult, we can't rely purely on direct numerical simulations. Partially because we know that dynamo models can't run in a parameter regime which is actually Earth-like. It's approaching Earth-like, but we're not quite there yet. And even in the wrong regime, running these dynamo models for timescales that are long enough to be relevant for the reversals is really quite unfeasible. So the parameter that's generally used to describe how close the simulation is to Earth-like is the Ekman number, which tells us about the ratio of viscous forces to Coriolis or rotational forces in the system. And now because the fluid in the outer core is not very viscous, but is rotating rapidly, the Ekman number in the Earth is very small. It's of the order of 10 to the minus 15. And this plot is showing you the Ekman number that's been achieved by various different dynamo studies against the publication date, and it's from a review paper from 2013, which is why it's so well populated up to 2012. But what was interesting about this review paper is that they tried to extrapolate the trend of the Ekman number that's been achieved by different dynamo simulations, starting from the first one in 1995 by Glatzmeyer and Roberts, and made some estimates of when they thought we might achieve Earth-like parameters. And continuing on this trend, we should achieve Earth-like parameters by 2038. But arguably, the lowest Ekman number that we've achieved in full DNS, that's critical to keep in mind, full DNS, is an Ekman number of 10 to the minus 7. And by 2022, we should have achieved an Ekman number of 10 to the minus 10. So it seems that we are already falling short of this trend. So it's really important to think of other ways in which we can approach this problem. So what's the alternative? What we've been trying to do is to develop theoretical models to study the system statistically, with the idea of being able to incorporate the paleomagnetic observations to get some qualitative estimates of properties of the outer core and the fluid flow. So the advantage is, of course, that it requires minimal equipment. The disadvantage is that the system of equations is insoluble pretty much by hand. So what we need to do is to apply lots of sensible approximations and simplifications that hopefully give us some insight into what's happening. And what we decided to do was to focus specifically on the induction process and think about what are the properties of the magnetic field and how are they based on properties of the velocity, and in particular in the context of stochastic processes. So why do we think it's relevant to use stochastic models for the geodynamo? Well, if we look at the fluid flows that we see in the dynamo models that we're pushing more and more towards Earth-like, we see that those flows are already quite turbulent, and we expect that as we push them even more towards Earth-like conditions, they should become even more turbulent. And turbulence has been studied using stochastic models for quite a while. In addition, if we look at the record of reversals, here it's shown for the past 160 million years. I'm sure, as you all know, reversals are not regular. There's no periodicity to them. And we have these supercrons and then periods of rapid reversals. And all this suggests a somewhat random behavior. So how can we apply these stochastic models to the dynamo? The idea that we've been trying to use is to model the core flow as a random forcing with well-defined statistics. So what do I mean by this? We look at the induction equation, which tells us about the rate of change of the magnetic field in time, which depends on the induction advection effects with the velocity u, and also on the diffusion in space with some diffusion constant eta, which is the magnetic diffusivity. And what we do is say this velocity u is essentially a random field, which is drawn from a well-defined probability distribution. And then we want to understand the averages of the magnetic field that emerge from choosing random velocities. And the probability distribution that we use for this is a Gaussian distribution. This is really just for simplicity and for making the calculation tractable. And what does that mean? It means that the probability distribution of this velocity has the following form. So it's an exponential with a quadratic term in the velocities. And the velocities talk to each other via this correlation function, which depends on space and time. Now, that's already quite a simple model, but we need to make even more assumptions to try to make progress. And what I'm giving you here is sort of the first pass at the problem. So the simplest possible assumptions that we can make, which we hope in time to relax to make the problem more Earth-like. But to start with, we are assuming that the mean velocity, so if you average the system over many different realizations, is on average 0, so there's no preferred direction, which probably is not the case in the Earth, but choosing a mean velocity is a very tricky problem because we don't really know what the velocity in the core is. We're not working in a sphere, but we're working in all space. Again, of course, this is not the case we have in the core, but qualitatively, it might give us some interesting insights into the problem without the details of the geometry. And third, we are assuming that the turbulence is isotropic. Now, this is also probably not a fantastic approximation because we know that in rapidly rotating fluids, the fluid tends to align itself in columns parallel to the direction of rotation. And that will break the isotropy. in the fluid probably. But for now, we're just looking at the simplest possible case, which is that of isotropic turbulence. So that's the basic setup and assumptions of our model. And what we want to know is how the statistics of the velocity influence the statistics of the magnetic field. And in particular, we're interested in knowing about the variability in the magnetic field as a function of the variability in the velocity, because we think this is one of the most important parameters for understanding reversals. So having assumed the velocity statistics, we've assumed that the velocity comes from that Gaussian distribution. We want to solve for the magnetic field probability distribution, because this probability distribution allows us to find averages of any observable of the magnetic field. So here, O of B is essentially any function of the magnetic field. It could be the magnetic field itself, if you want to solve for the average of the magnetic field. It could be the magnetic field squared, or it could be a more complex function of the magnetic field. And to find these averages, essentially what you need to do is integrate over all possible magnetic fields, this observable weighted by the probability of obtaining a certain magnetic field. And this is the approach that we've taken in the past. And for averages of the magnetic field, it works quite well. And it produces results that in the correct limits are consistent with, for example, mean field theory. The idea is then to combine these results with paleomagnetic data to then back out estimates of properties of the underlying core velocity. Now, when we're looking at variability, which is what we are interested in for the reversals, this approach becomes quite difficult. The main complexity comes from the fact that we're dealing with three-dimensional vector fields. And when you're trying to calculate these squares, then you're having to deal with 6 spatial coordinates, and it becomes quite tricky to do. So more recently, we've been trying to simplify the process even further and think about the kind of paleomagnetic data that's available to us and that we've used in the past to try to make these connections. And in the past, what we used was the PAD-M to M model. So essentially, we've been looking at the amplitude of the axial magnetic dipole moment over the past 2 million years. So we have this time series, but simply for the axial magnetic dipole moment. So in principle, we don't really need the full complexity of the magnetic field. So this is the definition of the axial dipole moment. And since it's a scalar, we were hoping to be able to find an equation that represents just this instead of having to compute the full magnetic field through the induction equation. However, there is an interesting but quite unsettling fact, which is that if you try to take the time derivative of the magnetic moment and substitute the time derivative of the magnetic field with the induction equation, the term that depends on the velocity actually goes away. It vanishes because of the no-slip boundary conditions at the core mantle boundary. So in fact, you find that if you're looking at the time derivative of the magnetic moment, it depends only on the magnetic field diffusion. So this is quite strange. I don't think it means that the magnetic moment does not depend on the velocity, but it does mean that it is difficult to relate these two quantities. So we're still trying to understand how we can make a connection between the two and still work with the scalar equation. But in the meantime, we've considered a test case for a problem that has strong similarities to that of the magnetic field, but is a scalar field, and we definitely have an equation for it, and that's the temperature, which is still relevant for core convection or any convection, in fact. And the problem that we've considered is that of thermal convection in a randomly forced fluid. And just for ease of explanation, let's assume that we're looking at air in a room. Okay, so what we want to understand is how does the temperature field evolve if we have a source of heat, say in this room, which heats the air parcels, but we also have something that is randomly forcing the fluid. And just because this is a toy example, I can take anything to be that random forcing, so why not take something that's a bit like a Maxwell demon? In Maxwell's own words, some being who can play a game of skill with the molecules. So imagine you have lots of these little demons peppered around the room, and they can essentially blow air in random directions whenever they please. So that's the random component of the fluid flow. Now, in the absence of these demons, if we were to measure the temperature in some place in the room after this heat source has gone off, what we would expect to see is essentially the temperature gradually increases until we reach an equilibrium temperature. However, in the presence of these demons, we might see a much more exciting, you could say, temperature profile, because if the demons blow hot air towards the thermometer, the temperature might suddenly go up, then cold air, and so on and so forth, until we equilibrate back to the equilibrium temperature. So in mathematical notation, what does that look like? We're trying to understand the time evolution of the temperature field T as a function of this velocity u, which again is a random velocity drawn from a well-defined probability distribution. And it's also diffusing with a thermal diffusivity constant kappa. So again, the probability distribution from which the velocity is drawn is taken to be Gaussian. And in this case, we take this correlation function to have a very simple form. It's a delta function on time. It has a spatial correlation function gamma, which depends only on the distance between 2 points. So there are no special points in our room. All the correlations depend just on the distance between 2 points. And its index structure is essentially isotropic. So within the context of this little example, what does this correlation function mean? So the delta function in time means that each of these little demons can decide to blow air at random times, and it doesn't care about when other demons decide to disrupt the airflow. The correlation in space means that the demons are aware of each other's positions and tend to blow the air more strongly when they're close to each other. And the delta function essentially means that the direction in which they decide to disrupt the air is random. So the quantity that we are interested in is trying to understand the variability of the temperature field. So we need to calculate these two quantities, the average of the temperature squared and the square of the average of the temperature. So let's start with the average of the temperature, which is the simpler of the two. So the idea is to run this system over many different iterations, and in each iteration, the configuration of demons will be different. And we are always measuring the temperature at a thermometer, which is at some place X in the room compared to the source, which is at X naught, at some time T after we've applied the initial heat source. So the temperature that we will measure at this thermometer is the mean of all the different temperatures that we measure throughout the system, throughout the different iterations of the system. Now, it turns out that this mean is actually equivalent to the probability that an air parcel will make a random walk from the source to the thermometer in time t. And this is very useful for us because it allows us to use path integral methods to understand these probabilities and to make use of a vast literature of physics and maths to attack this problem. Now, in the case of calculating the temperature squared averaged, we no longer have to take into account only one particle path, but we need to look at the path of two particles. And the challenge here is that these paths are not independent. They're correlated because the demons know about each other's separation. So this makes calculating the temperature squared quite a bit more complicated. So I'm giving you here the expressions that we've calculated for each of these quantities. And I just want to point out some interesting features about it. So if we look at the average of the temperature, you can see that it depends on the path integral of this path A that the particle takes from the source to the thermometer. And what is interesting is that it has exactly the same form as a random walk, but with a modified diffusion coefficient. So it no longer depends only on the thermal diffusivity, but it also depends on the correlations of the velocity at the source. If we look at the temperature squared, we now don't depend only on one path, A, but we depend on this vector path, capital A, that depends on the paths A and B. And these don't simply multiply each other, but they're related via a matrix M that depends on the correlations of the velocity. So essentially, this is telling us that this quantity depends on how close in space the two paths come together. And this makes calculating this quantity much more difficult. So let's take a closer look at this matrix M. So in general, it takes this form. So again, it depends on paths A and B. So this makes computing this quantity very complex. But if we look at the matrix in the short and long time scale limits, we can make progress. So let's consider the long time scale limit first. If we wait long enough, the velocity will essentially become decorrelated. And what we have is essentially diffusion of two independent paths. But in this case, the mean of the temperature squared and the square of the average of the temperature become equal. So we have no variability in our system. So this is not a very interesting case to consider. If we look at the short time scale limit instead, our matrix reduces to something that still depends on the correlations of the velocity and has off-diagonal components, which gives us a variability. So this is an interesting and non-trivial case to consider. Now, there's been a lot of maths in the last few slides, and I apologize for that. But let me give you an intuitive picture of what we're looking at. So we have, again, this heat source, which has some initial intensity T0, and we started at a time T equals 0. And we have air parcels around the heat source, which are gonna essentially heat up due to that initial source. And if we wait long enough, the temperature will equilibrate to a slightly hotter temperature. Now, in between these two scenarios, there must be a time where the variability of the system is maximized. And that's what we're interested in calculating. What is this tau max at which we have a maximum spread in the temperatures of the air parcels in the room? So using the expressions that I showed you previously, we can calculate this and find asymptotic solutions for the short timescale limit. So to first order in the correlations of the velocity, we find that that timescale, tau max, takes this form, and the variability has the following dependence. And these results actually make quite a lot of sense in the context of the picture that I've just been showing you, because if you consider a random walk, the dependence between the mean squared displacement and the time that you wait is indeed that the time depends on the distance squared from the source. The time scale to achieve this maximum variability will decrease if the thermal diffusivity is higher, because in this case, the system will equilibrate faster. So you'll have less time to achieve that maximum variability. And it also is inversely proportional to the correlations in the velocity, because if you can think of the velocity correlations at the origin a bit as the amplitude of the velocities. And if the velocities are faster, you might just think that you'll achieve the maximum variability faster. Now, the intensity of this variability obviously depends on the intensity of the initial temperature perturbation. It's also proportional to the velocities, because you can kind of think of it as how long does it take, well, as if you have a temperature disturbance, which is being carried by the velocities, you'd expect it to be larger if you have larger velocities. It's inversely proportional to the thermal diffusivity, again, because if the system equilibrates faster, you might expect that you might not be able to have the same amount of variability. And the dependence on the displacement is totally consistent with a diffusive Green's function. So I've given you a lot of information about the temperature field, which might be disappointing to a lot of you. So I thought for the last few minutes of this talk, I'd leave you with some insight on how this connects to the geomagnetic field. So this is a plot from a paper by Purnam and Buffett. And they, amongst others, have thought about reversals in the context of a double well potential. So the idea is that you have these two wells, which represent either the normal polarity or the reverse polarity. And you can model a reversal by thinking, what is the probability of jumping from one well, say in the normal polarity, to the reverse polarity? And what they found was that the reversal rate took this form, where x is essentially the dipole moment. So it depends on the average of the dipole moment squared and on the variability of the dipole moment. So clearly, if we were able, through finding an equation for the magnetic moment, to find these two quantities for the dipole moment, we would immediately have a connection to reversal rates, at least within this double well potential model. And what's interesting about that is that if we combine it with paleomagnetic observations, which tell us about the reversal rates, maybe we would be able to learn something about the correlations of the velocity that underlie these reversals. So that's the idea of what we're trying to do. And in principle, maybe this could also provide the basis for deriving scaling laws for the fluctuations, which might be quite interesting. So in conclusion, what we've been trying to do is to study these long time scale behaviors, especially reversals, from the context of the induction equation, and hopefully in the future also involving the Navier-Stokes. And we've been using these stochastic methods and investigating the statistics of both vector and scalar fields in turbulent fluids. For the simple case of the temperature, we're able to calculate the variability, and we are hoping to be able to extend this to the magnetic moment, and then try to combine that with paleomagnetic information to understand geomagnetic reversals better. Thank you.
Thank you, Daria, for your interesting presentation. I will open the floor for questions, so feel free to raise your hand or write a question in the chat. So we have a question from Richard Holm.
Mm-hmm.
Oh, I had an applause, but I'm happy to ask several questions as well, so I'll ask one and then shut up. So this is all about reversals. How about excursions? Is this kind of fitting in with the same kind of thing you can do here?
Yeah, I think it would be. You'd have to then, so the reversal has this sort of, within this simple model, you have this nice formula that tells you what's the reversal rate. So if you had something similar for an excursion, say.
Okay, so just in a box list kind of way. Okay, fine, yeah. Because in the last 100,000 years, monococcordus models are producing a variety of a number of excursions at different amplitudes, and therefore there actually is a background of how the field is varying. So there's a way to, I mean, obviously it's not the stochastic, but it's a way to kind of maybe mesh the observational and the stochastic methods if you look at excursions.
Yeah, I see. Yeah, that would be very interesting. Essentially, yeah, from our point of view, if you have some kind of model that connects these quantities, and then we have another model that tells you about how the variability is related to properties of the velocity and stuff, those are kind of the stepping stones. But yeah, if there is something that connects those, you could definitely use those as well.
Right. I have another question, but I will step back out of the way and let other people, and Daniel can call on me as and when if no one else perks up.
I have one question while we're waiting for Richard.
No, you don't want to wait for me. You talk.
It's actually a similar question, but the other direction. What about longer term trends and magnetic field behavior? I'm thinking like large changes to reversal frequency and dipole moment. For example, when we talk about inner core nucleation, can it tell us something about that as well?
Yeah, I mean, that's a good question. I think there have been attempts, to pinpoint that in the paleo literature and stuff. So I guess the thing is with this, you can make the relations as robust as the approximations that you put into it. But then when you're choosing the data, that's where you have to be a bit careful about what you're trying to understand. What I'm trying to say is, I think the best thing would be to put the longest time series into this and to try to understand average properties over the longest time scales. Obviously, having that really long time scale information is difficult, which is why we've looked at things like the PAD M2M model, because we have this continuous record over the past 2 million years. But yeah, I mean, what would definitely be very interesting is if we had the data to look at, oh, okay, what if we apply it just to 2 million years? What if we apply it to 4 million years? What if we apply it to the first part and the second part? And there you might discover some interesting features. I mean, obviously, you need to go much further back for the inner core nucleation. But in principle, if the data were there, yeah, that would be a really cool thing to do. Yeah.
Cool, thank you.
You've got a question in the chat, I think.
Yeah, we have a question in the chat from Jean. Nice talk. When regions are hotter in the core, how does it relate to local electrical conductivity?
Oh, see. Well, I mean, I'm not an expert on core conductivity, and I'd say we just take these parameters as sort of one single average parameter, so I might not be best placed to answer this question. I don't know if anyone else has a comment about this.
We have a question from Alexei.
Thank you. Thank you for your talk. And I have a question about the value of dipole moment, because the paramagnetic data says that there is some periods in not far a long time ago, a few million years, when the dipole moment was very high. It's above the 10 in power of 22, so about 12, maybe even more. And magnetic potential in this way is going to very high values. So can you explain the behavior in to the very high value of paleo axial dipole moment? Thank you.
Okay, so yeah, one thing that we would like to understand by computing this variability is what is the amount of change in the magnetic field that would make sense, which is consistent with just normal induction given certain parameters of the velocity. So while I can comment on individual events, the idea of the model would be to say, oh, is that very high value consistent with just random fluctuations, or do we need to invoke some other kind of process to explain it? So this is sort of the input to our models, so I can't really comment on what exactly is happening, but we would like to try to understand features like this with it.
Okay.
Richard, go ahead.
Okay, this is a left field question, which doesn't actually have much to do with most of your talk and has much more to do with my ignorance, I think. But you had a bit of vector calculus,
Yeah.
where you set things being dependent on diffusion only. Can you show
Right.
that again? So
Yeah.
this is the magnetic moment. So if I'm thinking in terms of a magnetic moment in terms of Gauss coefficients, are we talking this is the dipole or G10 or what is it?
This is the full magnetic moment, and then you could project it onto the one you want. I think, okay, so I've put it in general here, but yeah, you can think about it as the dipole moment with, yeah, you could
But
project it.
I suppose the integral is over the volume, so it's the dipole within. I mean,
Within
it goes to a
the,
surface integral, but it's within the whole volume.
yeah, within the conductive region, yeah.
Okay, I'm going to. Yes, I should know. I should have known this, but I didn't. You can tell Bruce that, and he will be utterly unsurprised that I've managed to ignore something fundamental. But you've given me something to think about. Thank you very much.
No, yeah, of course. I mean, honestly, I only learned about this relatively recently, and I think it's a very surprising thing.
Well,
It
I'm
has
very glad you told me. It still doesn't make up for the fact that I haven't thought about it in the last 40 years, which I should, or 35 anyway. But nonetheless, yes. Because obviously there's a difference between no slips and free slips and top of the free stream and stuff, but the no slip is the physical one. So yes, I will
Exactly.
ponder. Thank you very much. That probably wasn't what you expected from your talk, but nonetheless, it's made my brain work, which is quite rare
No,
these days.
I'm happy. I'm happy someone asked about this because, yeah, I still haven't fully wrapped my head around this. How is it possible that it doesn't? So if you take the second derivative, it does depend on the velocity, but it's just the first derivative doesn't. Yeah.
That's kind of odd, thinking about continuity in time. I'm not quite sure what that means, but because if you've got a second derivative, my brain hurts. That'll keep me busy for a few weeks, I suspect. Thank you.
We have another question from Alexei.
Yeah, if you don't mind, it's very interesting about the time dependencies. So as you say, there is a not for a long time your behavior you calculated, and does it have the shortest? What is the shortest time period when we can find the inversions or the high value changes in your model? I mean, we have some barriers, like the velocity of the conduction is limited. So the time for inversions and the changes in magnetic dipole moment it have the shortest, so there is not shorter than the sum there is a barrier which is cut the changes in dipole moment. So is do you looking for the times which is where your model is can explain the field behavior?
Right. So you're asking if there's sort of a time scale on the lower end below which our model can't capture the changes?
Yes.
Okay.
Yes. Thank you. I'm sorry for my English. It just
No worries.
not enough time to to practice.
Right. Yeah, I think yes, that's a good question. If you're applying this kind of stochastic framework, yeah, you need sort of to be considering long enough timescales that these averages make sense, right? Because of course it is a deterministic system. The idea is just that if you're waiting long enough, it's like having lots of different manifestations of the velocity, essentially. If it's turbulent, and so it's very sensitive to small perturbations, that means that it can change. The time scale over which that would be relevant, it would be then multiples of the turbulent timescales of the fluid flow. And so people have said maybe the overturn time is at least an indicator of what that timescale might be. And that's on the order of hundreds of years, maybe 150 years. So really compared to the paleo observations, it's a very short timescale. Yeah.
Thank you again. Thank you.
Okay, if there are no more questions, then I'm going to hijack the screen one more time. Just as a short outlook to what's coming up, we will be having a break for the EGU meeting, so we will not be back in 2 weeks, but we have 2 more seminars coming up in May. We're waiting for final confirmation of those speakers, but we'll let you know on the email list about who those speakers are going to be and what they're going to present.